lawyers know who you are. But soon they found the error in their way, and now they've actually released SDKs, software development kits, around the Kinect, and they're supportive of using it in other applications. So why is this thing so interesting to roboticists? It provides high speed, basically real time, 30 frames per second, high resolution 3D data. And oh, by the way, it costs $150. So that is 2 orders of magnitude cheaper than any previous 3D sensor of that capability. So that's really a disruptive technology for a roboticist. So consequently, it's seen rapid adoption, especially in the robotics research community. So up here on the top, you can see what's called a turtle bot. It's put out by a company called Willow Garage. Over here on the right is some research that we're doing in using that Kinect sensor to drive autonomous or fully automated manipulation of objects. Down here you can see a quad rotor, which has got a Kinect on top that's used for localization and mapping capabilities. So it's really been a boon for the research robotics industry. But we haven't seen much use in industrial settings yet. And there's probably a number of reasons for that. Initially, Microsoft wasn't supportive of it, so you don't want to put it into some sort of manufacturing environment where you have to support it for years. That no longer is the case. So we're starting to look at using it. In fact, we've got multiple programs going on right now that are looking at using it in industrial applications. It really is a game changer for the robotics industry. I wanted to show you one application of it. This is some research, again, coming out of Microsoft. This is out of their UK research lab. And it is being used now to build 3-dimensional models of environments. So the Kinect gives you a 3D map of the world. It gives you a single image. What you'd really like to do is build up a full 3-dimensional model of your world, sort of a static model. Essentially, what this thing is able to do with the Kinect and with these additional software implementations called Kinect Fusion, basically able to wave this the Kinect around and build up a full, real-time, 3-dimensional model of your environment. It really is visually stunning. It's a capability that doesn't exist in any sense today, certainly not for real-time applications. You can kind of see snippets of it, but imagine being able to wave this Kinect around the room and build a map of the entire environment, including the people in it. Really an incredible capability, and one that is going to change the game of roboticists, but also other applications. So imagine going into a plant where you need to install new equipment, and you need to map out that environment. Maybe you've got some as-built drawings, but they may or may not be accurate. So you pull out your tape measure, right? Start measuring piping, start measuring equipment layout. Well, instead of doing all that, imagine whipping out your Kinect and just waving it over this surface and being able to build up a 3D model that you can then pull into your CAD program. It's really revolutionary for a lot of different applications, and it's going to drive robotics in the future. Okay, so moving on to software systems. So I've kind of classified robotics software development in 2 different ways. So looked at industrial systems or industrial software development and the research robotics community. And these are 2 communities that are near and dear to me because I kind of straddle the line between them. So in industrial systems, you're dealing with sort of these proprietary environments which are provided by industrial robot vendors. These are people like Flannigan and ABB and KUKA, and there are a number of others. And for doing the tasks that those systems were designed for, that's fine. But if you want to extend the capabilities of those systems, it's very, very difficult because they are closed and they are proprietary, and you really don't have access to the interfaces that you'd like to extend the systems. So for example, if I wanted to hook that Kinect up to a classical industrial robot controller, it just couldn't be done or not done for any small amount of dollars. So it's been a very limiting situation, and that has really hampered the research community in applying their methods to industrial robotics. On the other side, you've got the research robotics community, and here you have very custom systems, right? Very few research labs, and these are mostly academic labs, are doing work in industrial systems because they're closed and proprietary. So you have many organizations, many universities who are developing custom hardware solutions and then building software stacks on top of them. And so while that's an interesting and flexible solution, it does have some problems too. So the first is highlighted there, reinventing the wheel. So if you build new hardware, you've got to build the drivers and all the whole software stack that sits on top of that hardware. And that's a lot of engineering work to do that. And then maybe you spend 80% of your time between building the new hardware and building all this software on top of it. And then you get to spend 20% of the time doing the really novel research. That's a big problem in research robotics, or it was until recently. The other problem with that is that you have the inability to compare results across different approaches. So let's say one organization is doing manipulation research and they've got some great new algorithm for path planning or grass planning or whatever it is, and you would like to validate those basic research results on another platform, or maybe just have another organization validate those results. Very difficult to do if you don't have some common framework for doing that development. You basically have to reverse engineer the whole thing yourself. So it just wasn't done. So consequently, what that did is it meant that nobody really knew how well these kinds of basic research in robotics worked in real-world applications. So this was a real problem for the industrial community as a whole for a long time. Both the proprietary and closed systems on the industrial robotics side, and then these very custom but always unique systems on the robotics research side. And then came along a company called Willow Garage. So Willow Garage is a startup out of Silicon Valley. They're about 60 people, and they're independently funded such that they have the ability to do basic robotics research. And their business model is somewhat unique. They are focused on developing general robotics capabilities and technologies with the goal of generating spin-offs. So they realized these problems that I had on the previous slide with these either very proprietary systems or these wildly custom systems, and said we need a common framework for doing robotic systems development. And so they took some of the work that was going on at Stanford Research, or rather Stanford University, and built what's called the Robot Operating System, or ROS framework as they call it. So ROS is supported by Willow Garage, but it's an open source program. It's free, it's BSD licensed, which means that it can be used for proprietary or commercial purposes. And if you talk to the Willow Garage folks, they describe it as kind of the combination of these 4 different capabilities or aspects. So at the top left there you have plumbing, and that's essentially the drivers. Right? That's what allows software to communicate with hardware systems and allows 2 different software systems to communicate with each other. So that's kind of the foundational stuff, the nuts and bolts that makes a robot work. Up here on the top right you have tools. So robotic systems developers need specialized software tools for doing their software development. So these are things like simulation environments and visualization environments and graphing tools and build tools, and all those are built into ROS. And then you also need capabilities. So what Willow Garage did is they looked out across the robotics community, and they basically took all these foundational capabilities in things like path planning and grass planning and navigation and machine vision and sensing and perception, and they built common frameworks or common libraries and rolled them into ROS. And then the last piece is this ecosystems. So not only did they make this open source and provide it to the world for free, they also support it. So they have things like wikis, they have online help, they have